Good morning. I'm Max He, a scientist in the CIG. This summer, I had a very smart and diligent student who can work with me. His name is Ahmed Tafti. He's a PhD student, PhD candidate at UW Milwaukee. He has done very good job in the past summer. Based on his progress, working progress, and very good results, we are also working on a manuscript. I'm really very happy to have the chance to work with Amanda. Let's welcome his presentation.
Thank you, Dr. Max. Hello, everybody, and welcome to the symposium. As Dr. Max mentioned, my project was data mining biomedical literature in the cloud. Here is the brief outline of the talk. I will first talk about background, objective, and methods, and I will finish with results, conclusion, and future work. What is literature mining and why we should bother this? Literature mining is a kind of data mining approach which is used to extract knowledge and information from text data, such as scientific articles. We have the problem of dealing with text data, and we hope to turn text data into high-quality information and operational knowledge. One application of literature mining is article classification. Let's say you have an article and you want to classify it into a proper class. For example, given an article, you want to know that is that article talking about diabetes, cancer, or asthma. If it's talking about cancer, is that related to lung cancer, breast cancer, or prostate cancer? If it's talking about prostate cancer, is that related to a kind of diagnostics, treatment, or prevention? Another problem is that we are facing with the issue of big data in scientific publications published in biomedical research. What I mean by big data is a data set that exceeds boundaries and sizes of normal processing capabilities. It forces you to take non-traditional technologies. This chart shows you the number of scientific articles published on cancer research, which is almost 1 million papers within the last few years. Literature mining and this large amount of text data would provide invaluable information and improve the quality of health care offered to cancer patients. So we need to tackle the problem of large-scale biomedical text mining. Large-scale biomedical text mining employs several computational technologies, including natural language processing, machine learning, big data infrastructures, and distributed database systems to convert the large amount of text into something that is more useful than raw text data. The objective of our project was to develop a scalable text mining framework for cancer research to first extract information, let's say breast, prostate, or lung cancer, and then develop prediction model to classify information extracted from tens of thousands of published biomedical articles downloaded from PubMed Central. In doing so, we wish to account for a big data set we had, big data infrastructures, as well as scalable machine learning techniques. Once we have done that, we wish to compare our proposed framework with two open source text classification tools called Weka Library and Tackleper tools. So we started with text preprocessing, in which we apply several text preprocessing tasks into the raw data we had. We parsed pre-categorized article into sentences. We then replaced special characters with blank spaces and made case normalization. After that, we removed duplicate characters as well as predefined stop words and rare words. And finally, we employed Potter algorithm to step all words in every single document. Once we have pre-processed text data, which normally contains string of characters, we have to convert it into something that proper to machine learning and classification task. N-grams, TF-ITF weighting, and bag-of-word representation are used in this way to train a classifier. I will talk about N-grams representation, TF-ITF, and bag-of-word representation in the following slide. Concerning computational linguistics, N-grams representation is a sequence of N terms in a given sentence. Let's say we have a sentence says the purpose of this study was to examine the incidence of breast cancer with triple negative phenotype, and we want to apply 2 grams representation. So unigrams would be the purpose of this study and so on, and bigrams would be the purpose of this study was to examine and so on, and it would be also purpose of this study was to and so on. TF-IDF stands for terms frequency and inverse document frequency. The objective of TF-ITF is to show you how a word is important to a document in a collection. For a term I in article J, TF-ITF weighting score equal to TF times log n divided by BF, where Wij refers to TF-ITF weighting score, TF refers to number of frequency the term I occurred in article J, N is the number of articles, and DF is the number of articles containing the term I. For example, suppose that you have 100 articles and you want to calculate TF-ITF weighting score for the term almost in article number 1, and also suppose that the number of frequency of term almost in article number 1 equals to 56. So the weighting score for term almost in article 1 would be 0. Once we have done with TF-ITF feature extraction, we get bag-of-word representation, which is proper for machine learning algorithm. Here you can see a very short version of bag-of-word representation. As you see, we have a set of unigrams here. We also have a set of bigrams here. And using TF-ITF weighting score, you can see the value of term almost would be 0 for every article in the dataset. After that, we apply 3 well-known machine learning algorithms, namely naive-Bayes, support vector machine, and logistic regression, to make a prediction model. We selected 75% random subset of the dataset to train a classifier, and we also selected 25% to test the classifier. In order to manage the big data we had, we employed Apache Spark and Apache Cassandra. Apache Spark is a fast and general engine for large-scale data processing, which is originally developed at UC Berkeley in 2009. It offers almost 80 high-level operators to make and create parallel applications. We also use Apache Cassandra, which is an open-source distributed database system designed to handle large amount of data, which is originally developed at Facebook. It offers high availability, high scalability, with no single point of failure. In this slide, you can see the block diagram of the proposed method. As you see, we first put unstructured, abstract, as well as full-text article into a Cassandra DB, which is divided into a small chunk within the memory. We also did text pre-processing, feature extraction, and making prediction model. In order to manage and handle big data, we employed several Apache Spark components. You see, Apache Spark Core is the main functionality of Apache Spark. mlib is the open source machine learning library of Apache Spark. Standalone scheduler allows to run jobs in first in, first out fashion. And Spark Streaming Real-Time allows to real-time streaming big data files. We develop the whole part of the framework with Java programming language as well as Scala programming language. Before going to experimental results, let's a little talk about the data set we had. The first data set includes almost 16,000 abstracts of articles published between 2011 to 2014. The second data set includes almost 11,000 full-text articles published from 2011 to 2014. And the last data set includes roughly 27,000 full-text articles published from 2009 to 2014. All articles downloaded from PubMed Central. I will first talk about the accuracy of the prediction model. Three common ways to examine the accuracy of a prediction model are accuracy, precision, and recall, where accuracy says what % of the prediction are correct, and precision says what % of positive prediction are correct, and recall says what % of positive cases are detected. Here, you can see the rate of accuracy, precision, and recall using different classifiers, including naive-Bayes, SVM, and logistic regression, as well as using different tools, including VECA library, TAC-LPL tools, and our proposed framework. These results obtained by the first data set. As you see, using naive-Bayes classifier, the rate of accuracy, precision, and recall are very close to each other, as well as promising. So in this slide, you can see the same result of naive-Bayes classifier, SVM, and logistic regression, as well as using same tools on the second data set. In this slide, you can see same results, naive-Bayes classifier, SVM, and logistic regression, as well as the same tools we had on the third data set. And you can see TAC-LPL tools was crashed on the larger data set. Here, you can see the rate of the accuracy of our proposed framework using different classifiers and different data sets. And you can see using naive-Bayes classifier, we got a better result. We got 96.6% accuracy using first data set. We also got 94.8% accuracy using the second data set, and got 95.1% accuracy using the third data set. The summary of accuracy is that the accuracy of prediction model using abstract is better than full-text articles, since abstract have less relevant features. Concerning the data set we have, the accuracy of naive-Bayes classification algorithm is better than SVM and logistic regression. Comparing to the well-known VECA library and TAC-LPL tools, our proposed framework generates promising results. We also examined the time efficiency of our proposed framework. As you can see, using the larger data set, our proposed framework takes almost 20 minutes to perform the work. VECA library takes almost 10 hours to perform the work, and as you can see, TAC-LPL tools crashed using larger data set. So the summary of time efficiency is that we did 30 times faster. Conclusions include using big data infrastructures. We developed a scalable framework for large-scale biomedical text mining. We work on almost 16,000 abstracts as well as 27,000 full-text articles for cancer research. We work on big data generated in biomedical research. We obtain about 96.6% accuracy using abstract and 94.8% accuracy using full-text articles. And we did 30 times faster compared with two other tool sets. As you know, cancer is a very malignant disease that causes millions of human deaths during the past decade. But yes, if we think together and we work together, we are bigger and faster than cancer. As part of our future work, we want to employ larger data set, for example, 100,000 or more full-text articles. We also like to try dimension reduction on the feature extracted from data set. We also like to develop a comprehensive tool set for large-scale text mining for cancer research. and we would like to make it freely available for research community. Before answering any possible questions, I would like to acknowledge many people without whom the project was not possible. I would like to thank Dr. Maxey, my mentor, Dr. Brilliant, the director of CHD, Merlin Stulin, and Kathy Marks, secretary of CHG. I would also like to thank program directors Bobby Burley and Dr. Macklin, and also like to thank Marshfield Clinic Research Foundation, SSRIP, and its donors. To me, their lovely personalities don't need any data mining approach. Thank you very much.